All right, let's jump right into this explainer. If you work with industrial enclosures, you already know the drill. Keeping your components cool isn't just about trying to extend their lifespan, it's about preventing a complete catastrophic system failure. So today, we're going to break down exactly how to calculate the required cooling airflow for an electronic enclosure. But more importantly, we're going to look at how to adjust those paper calculations for the harsh, messy realities of the field. Here's a quick look at our agenda for today. First up, we'll cover the heat trap. Second, we'll dive into the core airflow formula. Third, we'll tackle real-world cooling adjustments. And finally, we'll look beyond fans at IP ratings. Let's get right to it. Part 1, the heat trap. So why do these systems overheat so incredibly fast? Well, think about what's inside. Power supplies, drives, contactors, PLC modules, they're constantly dumping heat. Electrical enclosures are basically giant, sealed heat traps. Without some kind of active intervention, those internal temperatures will easily climb to destructive levels. For example, let's say it's a perfectly normal day outside, a warm 35 degrees Celsius ambient temperature. Inside that sealed enclosure, it can quickly skyrocket to a staggering 76 degrees Celsius, entirely from the heat generated by its own components. Heat always wants to flow from higher to lower temperatures, right? But when your cabinet is sealed shut and running heavy loads, that heat literally has nowhere to go. And here is the absolute kicker. Most of your PLC and industrial automation equipment, it maxes out at a 60 degrees Celsius rating. That means thermal management isn't just an optional upgrade, it is completely critical. In fact, many CPU modules will actually start to derate, meaning they actively throttle and lose performance if the ambient air around them exceeds just 55 degrees Celsius. If you don't calculate your cooling properly, you aren't just shortening the life of your gear, you're actively degrading its performance day in and day out. Moving on to part 2. The core airflow formula. So how do we actually figure out what we need? It comes down to a fundamental thermodynamics formula that uses the heat transfer rate to tell us exactly how much volumetric airflow is required. V equals Q divided by 1.08 times delta T. Let's break that down. V is your target cubic feet per minute, or CFM. Q is your total internal heat load in watts, and you get that by simply adding up the power dissipation of every single component inside your box. Finally, delta T is your allowable temperature rise. That's the maximum difference you can accept between the outside ambient air and your internal target temperature. Now, a quick heads up on that 1.08 constant. You've got to remember that this number assumes standard air at sea level pressure. It represents the volumetric heat capacity of air at about 68 degrees Fahrenheit. It's a perfect theoretical starting point. But what if your enclosure is sitting up in Denver at over 5,000 feet of altitude? Well, the air up there is thinner, meaning it holds less heat. In that specific scenario, you'd actually need to multiply your required airflow by a factor of 1.15 just to get the exact same cooling effect. Context here is absolutely everything. Consider how the math scales up in practice. Bumping your heat load from 100 watts to 500 watts, while keeping that same 10-degree temperature rise, multiplies your required airflow drastically, pushing it from roughly 9 CFM all the way up to over 46 CFM. As a general rule of thumb, you can expect to need about 1 CFM per watt of heat dissipation for every 1 degree Celsius of temperature rise. And remember, trying to achieve a 0-degree temperature rise is practically impossible. It theoretically requires infinite airflow. Usually, targeting a delta T of about 10 to 15 degrees Celsius is the sweet spot for a cost-effective design. All right, part 3, real-world cooling adjustments. Now we have to face reality, because a calculation on paper rarely survives contact with the real world. That rated fan airflow printed right on the side of the box, that was measured in a perfect zero-resistance environment. But your delivered airflow, the air that is actually cooling the cabinet, has to fight through serious system resistance. Inside a real enclosure, you've got thick wire routing, DIN rails, bulky transformers, and completely non-uniform flow paths. All of that static pressure severely throttles the actual performance of your fan. And it gets worse. Add a standard system filter into the mix, and you typically lose 10 to 20 CFM immediately, right off the bat, just due to pressure drop. And hey, that's when the filter's brand new out of the box. If you're relying on a fan rated for 50 CFM to deliver exactly 50 CFM into a filtered cabinet, your components are going to roast. So to compensate for all these real-world losses, engineers absolutely must add practical safety margins before making a final fan selection. Always add at least a 25% safety margin to account for dust clogging up that filter over time. Plus, you need to make sure your exhaust vents are sized correctly so you aren't choking the fan. A really good rule of thumb is a minimum of 1 square inch of free vent area for every 5 CFM of airflow.
And finally, you just can't ignore the environment outside the box.
Take the Turpin case study from 2024 as a prime example. This was an outdoor pump station in Xinjiang with a 1,580-watt internal load and severe solar exposure. Pushing hot 45-degree ambient air into that cabinet wouldn't cool a single thing. It proves that sometimes basic fan math isn't the final answer. The formula might say you need a certain CFM, but if the area pulling in is already hotter than your internal target, or if the sun is baking the metal surface of the cabinet to over 54 degrees, standard open airflow cooling completely falls apart.
Which brings us nicely to part 4, beyond fans and into IP ratings.
So what do you do when your enclosure literally isn't allowed to breathe? While forced convection, pulling air through the box, is powerful, bringing in outside air violates strict environmental sealing requirements. You're pulling in ambient air, which means you're also pulling in dust, oil mist, humidity, salt, or even insects. In a harsh industrial or outdoor setting, that contamination is going to destroy your electronics just as fast as the heat would.
If your application requires an IP65 or IP67 rating, your enclosure has to be sealed totally tight against both dust and water. That blocks convective airflow entirely. For context, the 6 in IP65 means it is fully dust-tight even under vacuum testing, and the 7 in IP67 means it can survive temporary submersion in water up to a meter deep. To pull that off, the entire housing, the sheet metal tolerances, the structural stiffness, the silicone gasket compression has to be perfectly co-optimized. Cutting a giant fan hole on the side, yeah, simply not an option.
For these tightly sealed systems, your thermal design has to pivot completely to conduction. You're using metal standoffs, thermal gap pads, or closed-loop air conditioners. Basically, you have to route the internal heat directly into the enclosure walls. This is exactly why extruded aluminum enclosures are so popular. They conduct heat beautifully and can be designed with external cooling fins built right into the frame, increasing the surface area to passively radiate that heat away. And if the ambient temperature is higher than your internal target, active closed-loop enclosure air conditioners or thermoelectric Peltier coolers are pretty much your only viable options left.
I love this quote from Norm Ellis at Machine Design because it hits the nail right on the head, perfectly summarizing our journey from basic thermodynamics to real-world application. The math, V equals Q over 1.08 times delta T, is just your first pass estimate. It gives you a baseline number. But it's your job as a designer to take that number and stress test it against system resistance, filter pressure drops, altitude, solar load, and your required IP ratings. So, as we wrap up, I want to leave you with this. When you are designing your next enclosure, ask yourself, are you sizing a fan for a perfect imaginary world, or are you actually preparing for reality? Because let's be honest, replacing a perfectly good fan is annoying, but replacing a melted PLC module, that's a very expensive mistake you only make once. Take a hard look at your current systems. Is your cooling calculation missing the big picture?